So now that we discussed the significance and the mechanism of the haloform reaction in the previous video, let's apply that to synthesis exercises. And so in each of these they say predict the major product that you get when you treat each of these molecules with bromine together with sodium hydroxide, followed by hydronium, so aqueous acid. And that's the recipe that we saw in the previous problem for the haloform reaction. So what this is going to do is turn our methyl ketone. And notice that we do have a methyl ketone. We have a carbon double bonded to oxygen with a carbon on each side. One of the groups on the side is a methyl group, so methyl ketone. It's going to turn that methyl group into a carboxylic acid. This base steals all three of the alpha hydrogens. As each one leaves, it becomes a nucleophile that steals a bromine. So you have three bromines there. That turns this whole group into a good leaving group. And then an OH does a nucleophilic acyl substitution, attacks the carbonyl carbon, tetrahedral intermediate, snaps back down and kicks the methyl group off. So if what I just said sounded like complete gibberish, you would want to go to the previous video where we walked through all of that step by step and explained what it meant. The effect of all of this is that you would replace the methyl group with an OH. And so if you take that same recipe and use it on a similar molecule, a methyl ketone, notice we have a carbon double bonded to oxygen with a methyl group on one side and a carbon on both sides, so that's a methyl ketone, you end up getting the same molecule, you just replace the methyl group with an OH. And the mechanism for that and everything we talked about in the previous video. If you have another molecule, again, doesn't matter what weird carbon chain you have, all you need is a methyl ketone, which we have here, a carbon double bonded to oxygen with a carbon on both sides, and one of those carbon groups is a methyl group, so that's a methyl ketone. Then you copy the same molecule just instead of the methyl group, you'll have an OH. That OH is ultimately coming from the hydroxide when it does a nucleophilic acyl substitution after this methyl group of the methyl ketone turns into a good leaving group. And so that is once you understand the concept behind it, predicting the product, the immediate product in a one-step reaction is pretty straightforward. You just replace the methyl group with an OH, otherwise the molecule stays the same. Let's try to incorporate that idea into larger synthesis problems, and that's what we're going to do in exercise 22.14. It says to just identify the reagents you would need in order to accomplish each of these transformations. Okay, well first with A, we see that in the original molecule there's just one bond to this oxygen. In the final, we have 3 bonds to oxygen. So we know, at the very least, whatever else we have to do an oxidation. Now we have a secondary alcohol here, and so we can use a strong oxidizing agent. It will take it to a ketone. So we can use something like sodium dichromate in water and sulfuric acid. Because it's a secondary alcohol, it will just take that to a ketone. Well, we at least have the carbonyl there. We at least increased the number of bonds to oxygen by 1. But you'll notice that this other group is an ethoxy group. What we have is an ester in this final product. And that's the only thing that changes. In other words, wouldn't it be great if we could turn this carbon into a good leaving group and then do a nucleophilic acyl substitution? And that's exactly what you can do. You can do that with the haloform reaction. So the first thing you would want is to treat it with bromine and sodium hydroxide, and then follow that up with hydronium. And that replaces that methyl group with an OH, just like we were drawing above in the previous exercise. So you can see that's what we were doing above. We just took that methyl group, replaced it with an OH by using this recipe. this haloform recipe. So that gives us the carboxylic acid, which isn't exactly what we want. We want the ester. We want to replace this OH with an OET. And so you can do what's called the Fischer Esterification. It's really just treating it with ethanol. That's your nucleophile that will come in and replace the OH. You do need an acid catalyst with that. So you can have H plus or H3O plus, either way, just so long as you have an acid catalyst. And you drew the mechanism for that on the last test. It involves a number of proton transfers, and then the standards for nucleophilic acyl substitution, nucleophilic attack, and loss of leaving group. So overall, and if you're conceptualizing it, this is your leaving group ultimately, and this is your nucleophile coming in. So you could see that replaces the leaving group in that nucleophilic acyl substitution. So overall here, the key to this was sort of seeing the difference in oxidation between the reactants and the products. That was the first big giveaway, 1 bond to oxygen, 3 bonds to oxygen, so we used a strong oxidizing agent. And once we had that, we had a methyl ketone. That should be like a key word that sticks out to you, that feature of a molecule. When you see that, you should think, I can turn that into a carboxylic acid through the haloform reaction, and from there, all of the carboxylic acid reactions and the derivative reactions are open to me. So basically, the whole world is open to you. So for this first one, a good recipe would be first sodium dichromate in water and sulfuric acid, followed by the haloform reaction, so Br2 and sodium hydroxide, and then hydronium, and lastly, Fischer esterification, so nucleophilic acyl substitution with an alcohol and the carboxylic acid, so that gives you the ester. And so that would be a perfectly good recipe for that one. Okay, let's try B. With B, you look at this, and one big thing that I see is, first of all, there's a carbon here, and that is sawed off and replaced with an oxygen. How do you break a double bond between carbons and replace it with an oxygen? That recipe you would have learned in the alkene chapter of Organic Chemistry 1. It's ozonolysis, and if you're not familiar with it, I encourage you to go and see the videos I made for that. The first step is to bubble ozone gas through your alkane, or alkene in this case, and then follow it up with DMS, dimethyl sulfide. And what that does is it breaks that bond apart, and where you had the double bond, you now have double bonds to oxygen. So you'd end up with formaldehyde. This carbon at the top would turn into formaldehyde. We're not interested in the story of that carbon chain here. We're interested in the story of the other one. And so this is the other molecule you'd get with that ozonolysis reaction. So in general, if you want to saw apart a carbon-to-carbon double bond, you can use ozone. It will replace the carbon-to-carbon double bond with a carbon-to-oxygen, with carbon-to-oxygen double bonds. And so that is useful because now we see that key word feature. We have a methyl ketone. So when we compare that with our product, that's awesome that we can see a methyl ketone because really we want to replace the methyl group with a chlorine. So we want to get rid of the methyl group. And we can do that by first turning this in to a carboxylic acid using the haloform reaction. So you'd treat it with bromine, sodium hydroxide. That gives you the good leaving group there, and then does the nucleophilic acyl substitution reaction, but it also steals off the hydrogen of the carboxylic acid, so you do an acid wash to put the hydrogen back on. So after those two steps, what you end up with is the carboxylic acid where you had the methyl group. So how do you turn a carboxylic acid into an acid chloride? There's only one way. You have to use the nasty molecule, thionyl chloride. Very toxic, very dangerous, but very useful. And so that's one possible synthesis for this. Now, you could have also thought of it backwards. You could have done a sort of retrosynthesis. You could have said, this is a carboxylic acid derivative. The only way I know how to make that is from a carboxylic acid. So you could have drawn the carboxylic acid and said, okay, I treat it with thionyl chloride and that'll do that. But how do I turn this into a carboxylic acid? From this chapter, you would say, well, I know I can make it from a methyl ketone, but how do I get the methyl ketone? I just have to saw that one carbon off by doing O's analysis. Okay, let's try C. C is fun because a star from a previous chapter comes back, sort of guest appearance. We have this acetal here. That's a carbon bonded to two different ethers. Two different ethers attached to the same carbon. That's your acetal. And you drew the mechanism for the formation of an acetal and the hydrolysis of an acetal. So it should make sense that the one thing you can do with that acetal is add some hydronium, and it comes apart and gives you a ketone. Now, who knows if that's going to be useful at all, but that's the one thing we know how to do with acetals. Okay, let's redraw this molecule. We've talked about this COOH before. It's an abbreviation for a carboxylic acid. Sometimes, just because of the way things are drawn, we don't see connections that we would see if they were drawn differently. So let's try drawing this out. Another way of drawing that is like this. So there's your COOH. You'll notice you have the 1, 2 carbons, 1, 2 carbons. Okay, well, now that we see this, we see a very clear connection between those two molecules. We have a methyl ketone and a carboxylic acid. That reaction is just the haloform reaction. You first treat that with molecular bromine and sodium hydroxide, and then you protonate it with an aqueous acid wash. So, hydronium ion. That's it. 3 steps. First, you hydrolyze the acetal, get the ketone back by adding aqueous acid. Then you do the haloform reaction, which requires 2 steps, adding molecular bromine and sodium hydroxide, followed by H3O+. And again, to know what those things are doing, I strongly encourage you to watch the previous video where we discussed that at length. Okay, so that is C. Last, let's look at D for this one. So with D, we see a nitrogen. The other nitrogen might stick out there, but they're really in different places. You might remember this original molecule is an imine, this one we're starting with. That's a sort of nitrogen version of a carbonyl. And that you also drew the mechanism for how those form, but you remember that every step of that mechanism was an equilibrium reaction, so it's reversible. All you have to do is treat that with hydronium and you hydrolyze it. So that would give you back your ketone. Okay, who knows if that'll be useful? Except it is so useful, because when you look at the product here, you see an amide, and in your mind, that should be categorized in the file called carboxylic acid derivatives. You think, carboxylic acid derivatives, wait a second, that reminds me of carboxylic acids. Maybe, who knows how, but maybe in some distant past, this was a carboxylic acid. And all I have to do is somehow turn it into that. Well, if it was, I could easily turn this methyl ketone into a carboxylic acid. That is the beautiful and magnificent haloform reaction that we've been studying for so long in this video and the last video. So first, bromine, sodium hydroxide, followed up by some hydronium, and that replaces that methyl group with an OH. So we get the carboxylic acid. Now, if you look at this, we do have a sort of leaving group here. It's not the best one, and we have sort of nucleophile that we know has to come in. The problem is that that you can't just treat this with excess ammonia. First of all, ammonia is a base, so if anything, it would just steal the acidic hydrogen off of the carboxylic acid and stop there. And so really, we have to turn this into a more reactive molecule before we do that. We know eventually we'll have to use the excess ammonia, but how do we turn this into a less acidic, more reactive molecule so that we'll get this in good yield? Well, the best thing, the most reactive of all the carboxylic acid derivatives, the sort of holy grail, are the acid halides, especially acid chlorides. And you can make those from carboxylic acids using thionyl chloride. So, if you treat that carboxylic acid with thionyl chloride, you get the acid chloride, and then you treat it with excess ammonia, you get the nucleophilic acyl substitution, and you get that beautiful amide as your product. So this involved reactions from several different chapters. The imine, hydrolysis of imines, that came from the ketone chapter. Using the methyl ketone, turning that into a carboxylic acid, came from this acid, or this alpha carbon chapter. And then these last two reactions came from the carboxylic acids and carboxylic acid derivative chapter. But you can see how it's all one world. They wrote it in a certain order, but the truth is organic chemistry is a book that's circular. You get to the end and you go, and it starts right back at the beginning again. Everything interconnects. Every page follows to every other page. The order that you study it in is largely just a matter of convenience. All of the different reactions interrelate. And so you can use them to make these very beautiful and elegant transformations. In this case, you turned an imine into an amide. So hopefully this gives you a sense of kind of the scope and a couple strategies for seeing these multi-step synthesis problems that involve the haloform reaction.